Hey guys, making a video on stopping distance. This came from a question about problem number 4 or question number 4 in the reaction time lab. So the one where you have to drop the meter stick or whatever you had, a ruler, through your fingers and time or figure out your reaction time based on how far the meter stick fell. Question number 4 said something about how would you figure out how far a car went if you were traveling 100 kilometers per hour and you had a certain time that was your reaction time. How far would you have traveled? That question was worded very poorly. I'm not going to answer it exactly in this problem. I'm actually going to go, this is a more difficult problem, and you can answer that question any way you'd like, but this video will help. I think what that question was getting at was if you were going 100 kilometers per hour for however long it takes you to react, how far do you go just in that amount of time? So all you do is, this would be, I'll do this problem over here. Some of the stuff's already filled in, but it would be steps 1 and 2 that I do over here. You would just plug your reaction time in, do steps 1 and 2, and sort of that's your answer for number 4 on that lab. I'm going to go one step further and do the rest of this problem, because these stopping distance problems are actually kind of interesting, because there are 2 parts to the problem. So this entire problem would not be something you're responsible for on that number 4, or really even in anything we're doing so far, but we can sort of get an example of a problem from start to finish about figuring out your stopping distance in a car. Alright, so this is our example problem. Again, if you can't read anything that I have on here, I'm going to post a PDF as I normally have. So the car is traveling at 100 kilometers per hour. That's not a unit we normally use, so our first step is actually going to be to convert that to meters per second so that we can plug it into equations. The driver sees the light turn red. If it takes the driver 0.25 seconds, so a quarter of a second, this is where, on question number 4, you would plug in your reaction time, whatever you calculated. Takes that long to hit the brake and then decelerates to a stop at 6 meters per second squared. So he goes 6 meters per second slower each second. How much distance do they need to stop? One thing I put up here is a velocity versus time graph. Now these I could tell were tricky based on some of the quizzes and stuff like that we've done. And they are. I think what we're used to is seeing position versus time graph, where a horizontal line means something's not moving, it's not changing its position. This light is really annoying over here. Let's just do this. Just for now. Alright, so if we're graphing position up here, not velocity, then a horizontal line means the position is not changing, so you're not moving. But in let me take these off so you can see, in a velocity versus time graph, a horizontal line, as long as it's not at the x-axis, this is supposed to be horizontal, it's not great, but a horizontal line means that the velocity is not changing. So they're still moving, but the velocity is a certain amount. Then a line like this means they're accelerating, they're changing their velocity. If this was position, we show acceleration by some curve, but that's not the case here. Alright, so there are 2 parts to this graph. This is actually the motion graph, the velocity versus time graph of this situation. Alright, for the first 0.25 seconds, the car is going constant velocity at 100 kilometers an hour. Now I crossed it out because we actually want it in meters per second. Whatever we get here, I'm going to put up here. So they're going that speed for the entire 0.25 seconds. Because remember, this is plotting how fast they're going. So at 0 seconds, they're going that fast. At 0.1 seconds, they're still going that fast. 0.2 seconds, they're still going that fast because they haven't started to slow down. The drivers are moving their foot over to the brake. Then, at 0.25 seconds, that's when they hit the brake and they start to slow down. The velocity is a little lower, and then a second later, the velocity is a little lower, and then a second later, the velocity is a little lower. And the slope of that graph is actually 6 or negative 6. If we say that they were going a positive speed in the first, then they're decreasing their speed by 6 meters per second every second. Now we don't know how long it's going to take them. We're going to figure that out later. So we don't know this, but we know the slope is going to be negative 6. The way to figure out a slope on any graph in physics, or really anything, to find out what that slope represents, right? We know that slope is change in y over change in x, right? Rise over run. Well, if we see something is actually, there's a physical quantity up here. Something's being plotted. The y, the change in y over change in x. So whatever is graphed up here, the change in that number goes on top. The change in whatever is graphed down here, it's usually time, goes down here. And then we see, does that mean anything? Is that significant? In this case, yes, that means acceleration. Change in velocity over change in time. That's our definition of acceleration. So in this case, we can figure out what the slope of this graph means by saying, okay, well, it's just whatever change in this over change in this is. Does that mean anything to us? In this case, it does. Sometimes it might not. All right, so this is the motion graph for this. Motion graphs are really helpful because instead of writing all of this, I can just show this graph and it describes the exact same motion. I know everything I need to know about it. All right, so let's move this over, start solving the problem. All right, our first step, like I said, is going to be to convert 100 kilometers an hour into how many meters per second is that of speed or velocity. All right, so what we do is we have what's called conversion factors. I'm going to multiply this 100 kilometers per hour by something to change the units. Now I don't want to change the actual speed. I still want it to equal the same speed. So the only thing I can multiply something by to get the same speed, it'll change the units, but it'll still be the same value, the same amount, is 1. I can multiply by 1 and I still get the same number. Well, what I can do is I multiply by a fraction where the top is equal to the bottom. If the numerator is equal to the denominator, that fraction equals 1. In this case, let's convert kilometers to meters first. 1,000 meters equals 1 kilometer. The top and bottom equal, right? So that's a conversion factor. I'm just multiplying this whole quantity by 1, really. So it's not changing the speed, it's just going to change the units. And it will change the number, but this speed and this speed we want to be equal. We just want to convert the units. All right. The reason I put kilometers on the bottom and not the top is because we want this to cancel out. We don't want kilometers, so I need 1 on top, 1 on bottom, so that I'm left with meters on the top. So that works. And then I want to convert hours to seconds. Well, I know I'm going to have to cancel out hours, so I put that on top because this one's on bottom. I need 1 on top and 1 on bottom if they're going to cancel out. And then I can just look up how many seconds are in an hour. They're actually 3,600 seconds in an hour. 60 times 60. 60 seconds in a minute, 60 minutes in an hour. And then I just multiply this. 100 times 1,000 divided by 3,600. This is useful in chemistry. We don't do it a lot. We don't do it a lot in our class. But that'll be really useful. You do that a lot in chemistry. The reason we do it this way is instead of just guessing whether to multiply or divide, right? If you're converting from feet to inches, you know you have to divide or multiply by 12, but sometimes you don't know which way. This is a way to sort of, it tells you which way to do it. Do you multiply or divide? Just do it this way and it'll tell you. All right. So 100 times 1,000 divided by 3,600 is, I did this earlier, is 27.8 meters per second. So 27.8 meters per second is the same speed as 100 kilometers per hour. All right, now we can get into figuring out how far we go. Again, step 2 here. This is kind of going to be our answer for question number 4 on that lab. So in the first 0.25 seconds, this car is not changing its speed. It's not accelerating at all. It's going constant speed. So what we can do is we can just say, all right, the average velocity is 27.8 meters per second. The time that this car is traveling that speed, that same constant speed, is 0.25 seconds, right? And we just do a speed equals distance over time, or average velocity equals displacement divided by time. It doesn't matter. If we're using velocity, we have a direction here. That's the little plus sign that I have. But it doesn't really matter in this case. If something's going in a straight line and not turning or turning around at all, we don't need to worry too much about if it's speed equals distance over time or velocity equals displacement over time, because they're not turning. Direction doesn't really matter. But we can still have it, so we multiply both sides by time to get displacement. And it cancels out there, so we get displacement equals average velocity times time. If we multiply these two together, so we get 27.8 times 0.25 seconds equals about 7 meters. So in this first part of the trip, before the driver has even stepped on the brake, just in that reaction time, they've already gone 7 meters. Okay, which is like 25, 24, 23 feet, somewhere around there. So without even stepping on the brake, they've already gone 7 meters, just because of reaction time. So if you see a red light, it will take the car, again, if it's going this speed, it'll take the car 7 meters. The driver will already go 7 meters before they even start pressing on the brake, just because of reaction time. And this time might be a lot longer for you. Maybe it was shorter. I'm not sure. Okay. Now, we need to figure out, that's not how far it goes total, because while you're pressing the brake, it's still traveling a certain distance. It's going a certain displacement. You're slowing down, but you're still going a certain distance in that time. So we want to figure out how far it's going while it's accelerating. So we plug in our 27.8 for its initial velocity. That's how fast it was going before it started to slow down. Its final velocity is 0 because it says it gets to a stop. That means the final speed is 0, final velocity is 0. And we want to know how far it goes while it's accelerating. The 7 meters that it went in the first part of the trip have nothing to do. We're sort of cutting the problem right here and now just doing this part.